Anyway, just going back to what we have with absolute value equations, and we have on page 70, okay, and we have in the mix, okay, so we have with number 90, okay. Okay, so we're looking at solving for t, okay, whereupon we have 4 times the absolute value of 2t plus 7, okay, followed by the addition of 2 is equal to 22. Okay, so looking at what we have in the setup, okay, so if I take 2 away from both sides, and again, I'm going to isolate the absolute value of 2t plus 7, and again with the grouping symbols that denote absolute value, I cannot treat as I would brackets or parentheses. So I'm not going to distribute 4 over all of 2t plus 7. So working around the absolute value term, so we have 4 times, okay, the absolute value of 2t plus 7, okay, is equal to 20. And now taking care of the coefficient 4, which will be done by division. And we have in the process, so the left-hand side becomes the absolute value of 2t plus 7, and 20 divided by 4, okay, so this is going to be 5. And so we're in the notation, okay, whereupon we have the absolute value of x, or I should say the format whereupon we have the absolute value of x is equal to k. Absolute value of x is represented by the absolute value of 2t plus 7, and k is represented by 5, and k should be a non-negative value, which 5 is going to be. And once I look at solving for t, as I take out the expression from the absolute value bars, again, 2t plus 7 is going to come out to 2 possible values, and it will be those amounts that will be 5 units away from 0, and those will be both positive and negative 5. Okay. So the values of t that will create a situation where 2t plus 7 is going to have an absolute value of 5, okay, they will stem from setting 2t plus 7 equal to negative 5 at the lower end, and 2t plus 7 equal to 5 on the upper. So for what we have now, in looking at solving for t, and we have for both equations, I'm going to take 7 away from both sides, and so we have for t such that 2t plus 7 is equal to negative 5. I'm going to have 2t is equal to negative 5 minus 7, which will be negative 12. And for 2t plus 7 equal to 5, taking away 7. So we have 2t is equal to negative 2. And we have with division by 2, okay, we have the lower value that we have as a solution in t is going to be minus 6. And for the higher, I'm going to have negative 1. So there are 2 solutions for t, where we have at negative 6 and also at minus 1. And now, for what we have in the case of number 91, okay, and we have for this particular problem, I'm looking at solving, okay, for the variable c, and we have in this one. All right, so I have negative 3 is equal to the negative of the absolute value of c minus 7, followed by the addition of 1. And I'm going to isolate, okay, the absolute value of c minus 7. Okay, first of all, I'm going to undo the addition of 1 by moving 1 by subtracting. So here we have negative 3 minus 1 is equal to negative 4. And I have is equal to the negative of the absolute value of c minus 7. And again, if I multiply or divide the equation by -1, and that is to just get rid of the negative sign in front of the absolute value notation. Okay, so for what is going to arise here is that we're going to have that 4 is equal to the absolute value of c minus 7. And here I can rewrite this. I'm just going to switch the order, like b is equal to a and going to a is equal to b format. So I'm just going to say that we have the absolute value of c minus 7 is equal to 4. And again, we have the absolute value of an expression equal to a non-negative constant. So there will be at least one solution. And so freeing up c minus 7, okay, this will be equal to the numbers with an absolute value of 4. So we have positive and negative 4. So we have with c minus 7 equal to negative 4, and also possibly c minus 7 equal to positive 4. And we have for both equations in one step, we will arrive at our respective solutions for c. Okay, so for c minus 7 equal to negative 4, okay, so we have c is equal to 3, and for c minus 7 equal to 4, we have that c is equal to 11. Okay, so we have two solutions for c with 3 and 11. All right. In the case of what we have, okay, for number 93, okay, this time we have the variable y to solve for. And so for what we have in this equation, all right, so we're looking at 2 is equal to 8 plus the absolute value of 11y plus 4. And if I isolate the absolute value of 11y plus 4, okay, just as I had moved 1 over, I'm going to do likewise with 8. Okay, so I'm going to subtract. And we have, in the rewrite, we have negative 6 is equal to the absolute value of 11y plus 4. And again, I can keep both sides as they are, but I'm just going to swap the location. So I'm just going to move the absolute value term to the left and the constant on the other side to the right. Okay, so I have the absolute value of 11y plus 4 is equal to negative 6. So I have, in this case, I have like the absolute value of x represented by the absolute value of 11y plus 4. And k, I have at negative 6. And again, k should be a non-negative constant. And because we have the number by itself away from the absolute value term to be a negative, automatically we have no solution. If I had 6 instead, again, I would be able to solve for y. But since we cannot have the result for an absolute value to reduce to a negative constant, okay, we have no solution. And in the case of what we have with number 94, we're looking at solving for z, whereupon we have 6 is equal to 7 plus the absolute value of 9z minus 3. And getting the absolute value term by itself. You notice we had before a number on the right hand side in front of the absolute value term, and we have this bit of history to repeat. So just as I had done with 8 in the previous problem, I'm going to do likewise with 7. So subtracting, we have negative 1 is equal to the absolute value of 9z minus 3. Again, I can just change the order, and if you notice right away, we have an absolute value expression set equal to a negative constant, and again, k cannot be negative. So just as what fate had awaited the result. Once we had k to be a negative, in this case minus 6 in number 93, we're going to have the same bit of history to repeat in number 94, because we're saying that k is equal to -1, and once again k cannot be a negative value. So 94 is yet another problem where there is no solution. And now for what we have in the case of 96, and this one you have a bit of a different dynamic that is created. Okay, and as if it were not enough, okay, to have one absolute value expression, we have for number 96, okay, we have two absolute value expressions, and these are set equal to each other. And for these absolute value expressions, now we're looking at solving for the letter A, and in the statement we had the absolute value of 2a minus 3, and we have is equal to the absolute value of a plus 2, and we have in the mix. Okay, so if I take out the absolute value notations, okay, now there'll be two results here for 2a minus 3. That the absolute value will be 2a minus 3. One is going to be positive and the other is negative. So you have the positive or negative of the quantity 2a minus 3. Okay, those will have an absolute value of 2a minus 3. As for a plus 2, the quantities that will have an absolute value of a plus 2, we have plus or minus, okay, the quantity of a plus 2. Now I'm going to copy this and just put down again. And for what we have in terms of processing and how to go about this, okay, so we have what I can do is that I can take the positive of one end and set up two equations where I had the positive end chosen is set equal to the positive of the other as well as the negative of the other. And what I mean by this, so I'm going to map together, 2a minus 3 and a plus 2. And also I'm going to map with the negative of the quantity of a plus 2. So just in this way I'm going to set this up. I need, now there are up to 4 possible combinations, but I need only 2 to get to both solutions. So I'm just going to map together. So you have the positive 2a minus 3 is equal to the positive of the quantity of a plus 2. And again, I had the positive of 2a minus 3 is equal to the negative of the quantity of a plus 2. And let me mention, okay, if I went with the other combination where I have like the negative of the quantity of 2a minus 3 is equal to the positive of the quantity of a plus 2, what I would have here is that you would have an element of redundancy. Now you could work all 4 of these out, but you would have an element of repetition. So you need, out of all 4 combinations, you need just half, like positive, 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 negative in the setup. Okay. And so just working what we have here, and we have for the first, okay, so no sign changes here. So you have 2a minus 3 is equal to a plus 2 Okay, so you have like terms on opposite sides, and here I can combine the terms in A, and I'm going to do this by subtracting A on both sides. So you have 2A minus A becomes A minus 3 is equal to 2, and if we have that A minus 3 is equal to 2, it's going to follow that A is equal to 5. Now, and mapping together a positive of 2a minus 3 with a negative of a plus 2. I have for this next go round with the distributing, so we have 2a minus 3, and then we have the negative of all of a plus 2 is going to be minus a minus 2. And so we have two sets of like terms. And if I combine what I have in the variable a, so I'm going to take out the smaller variable term, and this will be done by adding a to both ends. So we have 2a plus a is going to be 3a. We have minus 3 is equal to negative 2. And here we have a two-step linear equation. So if I add 3 to both sides, so we have that 3a is equal to 1, and we have a division by 3. Okay, a is going to come out to 1/3. And I can sort of check the results here. If a is at 5, 2 times 5 is 10, 10 minus 3 is 7. And the absolute value of 7 is 7. And the right hand side, we have 5 plus 2 is 7. Absolute value is also at 7. So we have 7 is equal to 7. So 5 checks out. Now for 1/3, okay, 1/3 plus 2. Think of like 1/3 plus 6/3 makes 7/3. Absolute value of 7/3 remains at 7/3. Now for the left hand side, you got 2 times 1/3 is 2/3. And I'm taking away 3. Think of 3 as a fraction, like 3 is 3 over 1, which is going to be 9 over 3. And 2/3 minus 9 over 3 has become a negative 7/3. And guess what? The absolute value of negative 7/3 is also 7/3. 7/3 is equal to 7/3. And so we have with our solutions, okay, one we have with the integer 5, and the other we have with the non-integer fraction 1/3. And if I tried out these equations, I would have 5 as well as 1/3 all over again. All right. Now, for what we're going to soon look into is going to be radical equations, okay, that concern non-integer exponents. But now, before I get into that, okay, now we had the other day looked at a problem that had two radical terms in the same kind of root, and I held off on this, and that was like the problem 110, okay, from the previous set, and I'm kind of use this as kind of a bridge to our next topic, and just kind of going back. So we have with what was the square root of d plus 4. And we have minus, okay, the square root of 6 plus 2d is equal to negative 1. Okay, and now for this one, okay, I can isolate either of these two radical expressions. In this case, I'm just going to isolate the square root of d plus 4. So I'm going to add the square root of 6 plus 2d to both sides. And we have, at this stage, we had the square root of d plus 4 by itself. And we have is equal to negative 1 plus the square root of 6 plus 2d. Okay, now I'm going to free up d plus 4 from the square root upon taking the square of both sides. Okay, so left-hand side is going to be d plus 4. And for what I'm going to have to the right, okay, so you have negative 1 plus the square root of 6 plus 2d times itself. Now, so we have in the process, so if I'm looking at foiling out, so you have -1 times -1 is 1. Outside product will have the negative of the square root of 6 plus 2d. Inside product will have another negative square root of 6 plus 2d. And the last term, you have repetition. We have the square root of 6 plus 2d times itself. Alright, so we have in the setup, okay, so you got 1. Now you have like radical terms that are back to back. You have minus square root of 6 plus 2d and another negative square root of 6 plus 2d, so you're going to have minus 2 times the square root of 6 plus 2d. And for the square root of 6 plus 2d squared, that's just going to free up 6 and 2d. And just combining, we have 1 plus 6 is 7. And we have minus 2 times, okay, the square root of 6 plus 2d, followed by the addition of 2d. Okay, and so just situating what I have over on the right hand side of the equation. Okay, so I'm going to isolate the radical. So that means I'm going to move both the 7 and the 2d over. Okay, so I'm taking 7 out. And also taking care of the 2d, so if I subtract, we have d minus 2d becomes negative d. 4 minus 7 is negative 3. Okay, it's equal to negative 2 times the square root of 6 plus 2d. And again, if I multiply or divide by negative 1, okay. Alright, so we have d plus 3 is equal to 2 times, okay, the square root of 6 plus 2d. Okay, so all the negative signs are changed. And so we got d plus 3 is equal to 2 times the square root of 6 plus 2d. And now we've got the radical term isolated. Now I could divide by 2, but if you do not want to work with fractions, you can just keep what we have and square out. Okay, now for d plus 3 quantity squared, again, if I FOIL out d plus 3 times itself, again, we have d squared, and then we'll have for the outside and inside products each at 3d, then we'll add up to 6d, and then we have plus 9. Here we have 2 squared is 4, square root of 6 plus 2d squared is going to be 6 plus 2d. And we have with the distribution, so you have d squared plus 6d plus 9 is equal to, and we have 24 plus 8d. Now we're looking at establishing this equation in standard form as a quadratic. So I can just move the 24 and the 8 times d. So we have d squared minus 2d minus 15 is equal to 0. And we have upon factoring, okay, so the quantity of d plus 3 times that of d minus 5 is equal to 0. And in drawing up, okay, the apparent solutions, upon once again utilizing the zero product property, if I have d plus 3 is equal to 0, okay, so I have d is equal to negative 3. If d minus 5 is equal to 0, okay, so we have that d is equal to 5. Okay. So just looking at what we have in the mix, let's see if I can. All right, so just sort of checking here. Okay, so if I have so if I were to check d equal to negative 3, so just think of it like this. You got with d at negative 3, so we have in our original equation negative 3 plus 4 is 1. And you got minus the square root. Now 2 times negative 3 is negative 6, plus 6 is 0. Square root of 1 is only 1. Square root of 0 is 0. And if I set d to negative 3, ultimately I'm trying to say that 1 is equal to negative 1, which it is not. So negative 3 is going to strike out. Now if I check d is equal to 5, okay, so you got 5 plus 4 is 9. And then we have 6 plus 2 times 5. Okay, so that is going to be 16. And square root of 9 is 3. And you got minus, now the square root of 16 is 4. 3 minus 4 is negative 1. And negative 1 is equal to itself. So that is going to be true. So 5 checks out and 3 does not. So for this equation, okay, that we have in D, we have one solution, and that is going to be at D is equal to 5. And I'll just mention now for radical equations that have two terms in the radical, chances are you're not going to see this at all in your exam, but I think it does appear among the ALEX homework items with the radicals. And now, yeah, very tedious, painstaking problem, to say the least. Now, for what we have in the crossover, and I kind of use this as a bit of a segue to our other types of equations we have coming up, and this will be for what we have in the case of equations with non-integer exponents. Okay, and you'll be looking at intertwining fractional powers and radicals. And an overarching rule of thumb, okay, so if you have a base to a fractional power, so you have a to the m over n, that is going to be equal to the nth root of a to the m. Okay, so for fractional powers, okay, the denominator defines what kind of radical it is going to be. And let's say that just taking for what we have among the examples here, going from, let's say, from exponent to radical. If we have something like x to the 3/2. Okay, so n is going to be at 2, m is going to be at 3. Here we have a represented by x. So you have like the second root of x to the third. And again, you'll see in most books anyway, you'll see it's just the square root of x cubed. And if I have, something like y to the 7/3. So here we have 3 at n, and this signals that the type of radical we are dealing with is going to be a cubic root. And we have for a to the m, that is going to be y to the 7th. So we have the cubic root of y to the 7th. And let's say if I have something like z to the 5/6. So the type of radical is going to be a 6th root. And we're looking at that of z to the 5th. Okay. Now, on with equations with non-integer exponents. And let's say we are looking at solving for x. And we'll say just to sort of kick things off. Okay, if I'm looking at x raised to the 1/2 power is equal to 8. Okay, so I have x to the 1/2 power is equal to 8. Okay, and if I write the x to the 1/2, okay, as a radical. Okay, so again, I'm just kind of repeating here. So I have the second root of x to the 1st is equal to 8. Okay, so that's just the square root of x is equal to 8. All right, now here we have an even root radical expression, and again, an even root radical cannot reduce to a negative constant on the basis of the principal square root rule. Okay, and here we have a positive 8, so we can proceed to solve for x. So I can take care of the square root upon squaring both sides. Square root of x squared becomes x, and 8 squared becomes 64. And again, square root of 64 is equal to 8. And if you were to test out, I'm just going to mention right quickly, if you have like 64, and I know with a lot of the TI models and those of other calculator brands, that if you have like 64 and you're looking at raising to the 1/2, do not forget to put fractional powers in parentheses. If you don't, you're going to get an entirely different readout. So for 64 to the 1/2, that should come out to 8. All right. And let's say that if I have, let's say we have, for instance, if I have the quantity, now say I have 2x plus 2 to the 1/3, and we'll say that we have plus 9 is equal to 5, and I'm looking at solving for x. What I want to do here is I want to get this exponential term by itself. So we have, for the setup, I want to undo the addition of 9 by taking 9 away from both sides. So 2x plus 2 to the 1/3. 5 minus 9 becomes negative 4. And if I rewrite the quantity of 2x plus 2 to the 1/3 in radical terms, so I'm looking at the cubic root of 2x plus 2 is equal to negative 4. Okay, so I got a odd root radical expression set equal to a negative constant. Now, if I had like square root, fourth root, any other even roots, there would be no solution, since even root radical expressions cannot reduce to negative constants. But again, the principal square root rule does not apply to what we have in odd roots. Okay, so I can proceed, and if I take the cubic root, 2x plus 2 equals negative 4, and raise both sides to the third power. So the left-hand side, okay, so you have third power, cubic roots, those portions cancel each other. So I got 2x plus 2. Now to the right, have negative 4 to the third. So that'll be negative 64. And if I take 2 away from both sides, so 2x is equal to negative 64 minus 2. Negative 64 minus 2 becomes negative 66. And so we have here that x is equal to minus 33. All right. And okay, so you had, again, just a potential focus with the principal square root rule. And let me kind of give you one here. If I've got say if I have x minus 5, and we'll say that we have to the 3 halves plus 9 is equal to 2, and I want to get the expression that we have in the variable by itself. So taking 9 away from both sides, so here I have x minus 5 to the 3 halves is equal to negative 7. Okay, so far so good. But now as I'm looking at converting from non-integer exponent to a radical, so I have the square root of x minus 5 raised to the third. Okay, and I have is equal to negative 7. And guess what? I have an even root radical, but I have a negative 7. And even root radical odd expression cannot reduce to a negative constant. So for this third instance, we have no solution. Okay, now special dynamic, okay, that we have here. And give you just I'll say something like we have just x to the 3 halves is equal to 8. Okay, so I have x to the 3 halves is equal to 8. And if I translate what I have here in x in radical terms, so again, this is going to be the square root of x to the third is equal to 8. Okay, so I got x cubed within a square root. Now, the work can start to get a bit crowded. Even when you're trying to clean up what is on display. Okay, but now, here I can get rid of the square root upon squaring both sides. So left-hand side, okay, now the square root and the square cancel each other out. So left-hand side becomes x to the third. And for 8 squared becomes 64. Now, in terms of the follow-through, now when we had like the square root property of equality, like x squared is equal to p, x equal to plus or minus the square root of p, that rule applied for even valued powers. But now for odd powers, for what we have in the case of x cubed, I'm just going to eliminate the exponent. Now if you notice, we took exponents to eliminate radicals, and all of a sudden we're shifting gears, or we are doing it the other way around. That is, taking radicals to eliminate exponents. So it's almost like jerking motion, just kind of twist and turn. And here we have for the cubic root of x to the third. Okay, so this will go to x, and for the cubic root of 64. Okay, now 64, special kind of number that is both a perfect square and a perfect cube. Okay, and 8 times 8 is 64, and that number times itself, that would give you 64, is going to be at 4. Okay, so we have, and again, just going back, you have an even root radical expression that reduces to a positive constant. So there was going to be a solution for x, and again, that value comes out to 4. All right, and now, case we have now, it's going to be where the square root property of equality can come in, and say if we have x plus 5 raised to the 2/3, and we have set equal to 4. Okay, so just rewriting, okay, going from exponent to radical. Okay, so again, we had the bottom number to be 3, so this is going to signal that we have a cubic root so the cubic root of the square of x plus 5, okay, is equal to 4. Okay. And again, just as I squared to get rid of the square root, and I'm going to cube both sides of the equation to get rid of the cubic root. Again, the word does get a bit crowded. So I'm cubing to get rid of the cubic root. So the left-hand side, okay, so this will become the square of x plus 5. And again, we just reduce the cubic root of 64 to 4. Now I'm looking at 4 to the third, which will go to 64. Now I'm at this phase where I have an expression to an even power set equal to a constant. And if you recall the square root property of equality, say we have like x squared is equal to p, x goes to plus or minus, okay, the square root of p. And so here we have x plus 5 squared. So x plus 5 is equal to plus or minus, okay, the square root of 64. And we have plus or minus 8. And setting x plus 5 equal to negative 8, as well as positive 8. And we have in both equations, we'll be looking at getting x by itself upon taking 5 away from both sides. And so for x plus 5 equal to negative 8, x will be negative 8 minus 5, which is going to be negative 13. And for x plus 5 equal to 8, so we have that x is equal to 3. So there will be two solutions in x with negative 13 and positive 3. All right. And I'll tell you what, just for the next few moments, okay. So let's see what we get with say we have x plus 5, and we'll say we have x plus 5 to the 2/3 is equal to 9, and we'll say that we have the quantity of 2x minus 2 to the 3/2 is equal to 8. Okay, for what we have in these two problems, okay, so we have the quantity of x plus 5 to the 2/3 is equal to 9. And now just rewriting what we have here as a radical. Okay, so you have the cubic root of x plus 5, okay, to the second is equal to 9. Okay, and again, if I take care of the radical, so I'm going to cube both sides. Alright, so if I cube, so I'm going to have to the left, I'm going to have x plus 5 squared, and 9 to the third. 9 to the third is going to be 9 times 9 times 9, which would be 729. And 729, kind of like the number 64 earlier, it is both a perfect square and a perfect cube. And here we have at this stage, okay, for x plus 5 squared is equal to 729. Again, we have with the square root property of equality. Okay, so I have with even powers. So I have going from x squared to x, and again have equal to plus or minus, okay, the square root of p. And here I'm going from the square of x plus 5 to x plus 5 to the first, and we have equal to plus or minus the square root of 729. And for what we have here, we have x plus 5. For plus or minus the square root of 729, okay, this will go to plus or minus 27. Okay, and so if I isolate what I have in x for both equations, so I'm going to take 5 away from both sides. So we have x equal to, now negative 27 minus 5 becomes negative 32. And for x plus 5 equal to 27, okay, so you're going to have the x is equal to 22. Okay, and so we have with our solutions, so we have negative 32 and positive 22. And I'm just going to restate, okay, since I had the cubic roots, okay, there was really no issue of whether the constant on the other side is positive or negative. Okay. Now for what we have in the next case, we have the quantity of 2x minus 2 to the 3/2 is equal to 8. And if I go from, again, exponent to radicals, now, so we have the square root of 2x minus 2 to the third, okay, is equal to 8. Now we got the square root of an expression to reduce to 8, which is not negative, so I can proceed. So take care of the radical by squaring both sides. Okay, so for what I have to the left, okay, so this is going to be the cube of the quantity of 2x minus 2. And 8 squared is going to be 64. Okay, and again, alright, so I just square to get rid of the square root. And now at this stage, with what is freed up with the cube of the quantity of 2x minus 2, I'm now going to take the cubic root to undo the exponent. Okay, so in this one, the left-hand side becomes 2x minus 2. And the cubic root of 64, okay, so that will be 4. And so for what I have in x, Okay, so if I add 2 to both ends, so I will have 2x is equal to 6. And with division by 2, so we have one solution for x, and that is going to be 3. Okay, now looking at what we have in the problems. Okay, from what we had from page 70. Okay, so we have with number 115, and we have in this case just looking at equations with non-integer exponents. And for the trio, okay, the last one I do want to mention is going to involve a special case, especially where radical reduction is concerned. Okay, so you have 3x plus 1 quantity to the 3 halves plus 2 is equal to 66. And if I take 2 away from both sides, so I've got 3x plus 1 to the 3 halves, okay, and we have 66 minus 2 is 64. Okay, so again, just rewriting as a radical, so I have the square root of the cube of 3x plus 1 is equal to 64. Again, a bit of history to repeat with squaring to get rid of the square root. Okay, so left-hand side, okay, so this will become the cube of the quantity of 3x plus 1, and for 64 squared, okay, so that is going to be 4,096. Okay, so for what I have on the left, okay, so you have 3x plus 1 is equal to, and 4,096, okay, just like 64 and 729 from earlier. Okay, we have 4,096 is both a perfect square and a perfect cube. Square root of 4096 is 64, but now the cubic root is going to be 16. And I'll just mention, okay, since I had converted to a square root of an expression reduces to 64, which is not negative, so I was going to have a solution. And so isolating 3x, so we have 3x is equal to 15, and we have with division by 3, okay, so we're going to have that x is equal to 5. And for what we have in the case of 116, so the quantity of 2x minus 1 to the 3 halves. Minus 3 is equal to 122. And adding 3 to both sides. So the quantity of 2x minus 1 to the 3 halves. Okay, so that is equal to 125. Okay. Now in terms of the numbers, they're different, but the process, the follow-through is going to be identical. Okay, so we're looking at squaring both sides. So here we have 2x minus 1 cubed, freed up from the radical. 125 squared. Let's have a really big number with 15,625. And taking the cubic root of both ends. Okay, so here we'll have 2x minus 1 freed up from the exponent after taking the cubic root, just like 3x plus 1 was freed up. And for the cubic root of 15,625, have another number, both a perfect square and a perfect cube. And the cubic root is going to be 25. And adding 1 to both sides. Okay, so we have 2x is equal to 26. And we have a division by 2. So we have for x, the outcome is going to be 13. All right. And now for 117, now we have with this particular special case. All right, have just a single variable in m to solve. Here we have m to the 3/4 is equal to 5. And if I convert from exponent to radical, so m to the 3/4, again, 4 in the denominator, indicates the type of radical we're going to be dealing with. So we have a 4th root, and this is going to be up m to the 3rd. Okay, and just as I have squared to get rid of square roots and cubed to get rid of cubic roots, I'm going to take both sides and raise to the 4th power, again, for the purpose of getting rid of the radical. So what I have on the left, okay, we have m to the 3rd. Now for 5 to the 4th, you've got 5 times itself, times itself, times itself, and that number comes out to 625. And to go from m to the 3rd to just m, so I'm going to be taking the cubic root of the terms in the equation. So we have left-hand side becomes m, and we have the cubic root of 625, and this is a radical that can be reduced. And just kind of show you what we have here in the perfect cubes. Okay, so you have like 1 to the 3rd is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. We got 6 cubed, 7 cubed, or like 8 cubed, 8 times itself becomes 512. And 9, which we have dealt with in its cube, we have it 729. And we have for 10 to the 3rd case, so that's going to be 1,000. Now for the cubic root of 625, again, not listed among the perfect cubes. But if I reduce what I have here, okay, so if I factor 625, now the highest perfect cube that will go into it is going to be 125. So I got the cubic root of 125 times 5. So I have the cubic root of 125 times the cubic root of 5. And so for the end result here, for m, so we have cubic root of 625, and again this would translate to 5 times, okay, the cubic root of 5. And for what we have in the next phase, okay, now we're going to continue on, okay, with radicals, and we've dealt with the real number system so far, and then there's another system, okay, involving radicals, and this will be with what we have in the complex numbers, or what some might commonly refer to as imaginary numbers. And I hesitate to call complex numbers imaginary numbers because there are some applications with complex numbers. Like in physics, you have positrons, and also complex numbers are used in electrical engineering. So it does have its purpose. It does have its purpose in scientific applications. And for complex numbers, now we have at the foundation, you have the letter I. Some books might have the letter J, but most will have I, and I is going to be in reference to the square root of -1. And if I were to square, I squared is equal to -1. And for complex numbers, okay, so you have, again, the foundation is I at the square root of -1. And to kind of give you a feel of what we have in working with complex numbers, and we have for expressing in terms of I, if you have, let's say, the square root of -25. Okay, and if I were to branch out, okay, now we got the square root of 25 times -1, and you can separate, say we had the square root of 25 times the square root of -1. Now the square root of 25 is going to be 5. Now again, the square root of -1 is going to be I, and guess what? The square root of -25 is going to become 5i. And let's say if we have something like the square root Now we'll say we have of -18. Okay, 18 is not a perfect square number, but it is reducible. So right now we have the square root of 18i, and the highest perfect square divisible into 18 is going to be 9. And the square root of 9 is 3. And times the square root of 2, and we have times I. And some like to write everything in front of the radical, so this could also potentially be expressed as 3i times, okay, the square root of 2. And say just another case here, if I have, say, the square root of -500. Okay. So if I branch out, okay, so I have the square root of 500. Okay, I'm just doing this very gradually. And now you have, again, have the square root of 500, I. And for 500, not a perfect square number, but it does have several perfect square factors, and the highest of which is going to be 100. So here, square root of 100 becomes 10. We have times the square root of 5 times I. And that becomes 10 times I times the square root of 5, or 10 times the square root of 5 times I. And where this I squared expression is going to come in, it's going to mention, okay, now the standard form of a complex number, okay, is going to be a plus bi. Now let's say that if we have, so again you have at the foundation, okay, so you have I is equal to the square root of -1. We have that I squared is equal to -1. And let's say that if I were to write the results in a plus bi form, and we'll say we have as a first case here, okay, if I have something like 3 plus the square root of -36, and I have plus 2 plus the square root of -100. What's going to happen here? Say if I reduce the square root of -36. Now, square root of 36 is 6. Square root of -36 becomes 6i. And square root of -100, that becomes 10i. And once I remove parentheses, so we have 3 plus 6i plus 2 plus 10i. And 3 plus 2 is 5. And 6i plus 10i, this is going to make 16i. And just to kind of squeeze in, let's see, I'm just going to draw this up. Okay, let's say if I have 3 plus 4i times 2 minus 3i. Okay, if I FOIL out, I got 6. 3 times -3i is a -9i. Inside product becomes an 8i. 4i times -3i is going to be a -12i squared. And again, I squared is equal to -1. I know we're getting a little bit pressed for time. You got -9i plus 8i is going to be a -i. And we got -12. Now I squared again is going to be at -1. So we have 6 minus I. -12 times -1 is going to be a +12. And 6 plus 12, okay, so that is going to be 18. And your I term is going to be negative, so the result here is going to be 18 minus I. Okay, and okay, so we're going to pick up next time. Have this up. Again, your ALEKS first part in section R5, the quadratic and rational equations, that will be due tonight. And the other part with radical and absolute value equations, that will be due Wednesday night. And the class activity set, okay, that will be due Saturday, January the 30th. And items to go ahead and be looking into, we have on page 80, we have numbers 13, 18, 42, 50 through 52, as well as numbers 55 and 56.